the other one quite gets where it was going. But all these estimates are approximate anyway. I've neglected small factors like that. If you want to work it out more exactly, of course, you can use a circuit simulator, draw up a circuit with various fan-outs and ratios and so on, calculate exactly what the delays are. But when you've done that, you can go back and compute what tau makes the estimates work out right. And therefore, there is, in fact, a number tau that makes these formulas make sense. And this is approximately the level of complexity that you ever need to get into to really evaluate the speed of your design. So here's an example. An inverter in a register typically has k equals 8, as I showed. It might be hooked up to 4 other registers, or maybe 1 register and a long wire that counts as a fan-out of 3. You have to count stray capacitance as fan-out also. That's where most of the complications come in, deciding when you can neglect that. A typical process, such as the one that Xerox's Microelectronics Center used to run in El Segundo before they improved it, had a tau of 0.3 of a nanosecond. I guess their new process is 0.2 or something like that, maybe better. Then if you apply this formula, k plus 1 is 9 and f is 4, so you get 36 tau, or 10.8 nanoseconds. And that's not bad for a fan-out of 4 and a MOS device, which people think of as a fairly slow technology. You get 10 nanosecond pair delay. If you look at average gate delays, you might be tempted to divide that by 2. Say the gate delay is 5.4 nanoseconds. That's probably fairly misleading because any given node has a rise time that's about twice the average. So the pair delay is a useful measure. So keep in mind this formula, k plus 1 f tau, for a pair of inverters. And don't forget that when you measure fan-out, you should include some measure of the stray capacitance in that. We'll talk about how you estimate that later. I think typically areas of wires count about 1 order of magnitude less than the area of the gate of a transistor. So you can go about, if you go that far on a chip, you can drive a device about that big without worrying too much about counting the stray capacitance. Scale that down a little. Okay. So you can do reasonably long interconnect without worrying about the strays. So let me just mention some more about NAND gates and/or invert gates. Doug mentioned earlier, you don't want to put 10 transistors in series on a NAND gate. Now here's part of the reason. Not only does the area get bigger, as I showed you before, with the increasing ratios, the widths of the pull-down transistors, but the main result of that area increase is that the fan-outs get larger. Look at this node here. This is an inverter driving an AND gate or a NAND gate or and/or invert gate, whatever kind of thing you want to put there with 3 transistors in series. If you assume equal load devices, equal impedance of the loads, equal geometric ratios, then this inverter, which only goes to 1 NAND gate, in fact has a fan-out of 3 because the device that it's driving is 3 times as wide as the driver device here. So you can't count fan-outs the same way you do in typical logic circuits. You have to count it in terms of gate area. So this thing that only goes to 1 place has a fan-out of 3. The device driving it might have a K of 4, and therefore the rise time on that node is 12 tau, which is not bad. That's reasonably quick. But you can see if you go to a 10-input AND gate here, it's going to be a lot worse. Now look at the alternative on the bottom. You can implement that same thing using NOR logic. That is, instead of that AND gate, you use a NOR gate and put an inverter on its input. Assuming this was fixed, I'll add this to make it a fair comparison. Now that node going into the NOR gate has only a rise time of about 4 tau. And in fact, the speed through that, even though there's more layers of logic, is probably faster than the and/or invert gate. Well, of course, the penalty is that there's more load devices in there, more area, and more power consumption. So you can see there's a definite trade-off there. But if you ever need a 10-input NAND gate, you better think carefully about how you implement it. Okay, the point here is that you got to count fan-outs of all sorts. Fan-outs due to how many devices, how big the devices are, and also the strays. And that's a big contribution to delay. It's usually the biggest factor in the delay formula, k plus 1 f tau. Okay. How much time do we have?
You have 15 minutes.
15 minutes? Okay. Let me point out that we have a homework assignment for tonight, which involves only the ability to design combinatorial logic using the assumption of switches or switches and loads. There's no requirement for tonight's homework that you know anything quantitative about this timing stuff and geometric ratios and so on. But I'll be going more into this first thing tomorrow morning. I want to give you an idea what we're going to be covering, and there'll be quite a bit in your reading about this kind of stuff. Okay, there's other kinds of delays to consider when designing a circuit. I'll give you just a brief introduction to them here, so it won't be a surprise when we cover them later. First thing, delays in wires. I mentioned two types here. The first we've already seen, that is the delay due to stray capacitance, which is added to the fan-out when you compute a delay on a node. The second type is really interesting. It's due to the distributed resistance, series resistance of a line, and its associated shunt capacitance. On a metal line, this is completely negligible because the resistance is negligible. But in a poly line, the resistance is considerably higher. Also in a diffusion line, it's considerably higher, and the capacitance is higher. So in two of the three layers, there's potential for quite a bit of delay in a signal propagating down these wires. Let me just draw a schematic. I'll give you a lumped approximation to what that distributed resistance and capacitance looks like. It consists of a series resistor, a shunt capacitor, repeated many times for each epsilon length of wire. Capacitance to ground or to wherever. For a signal to propagate in here, if you put a step function in here, you get roughly a first order, exponentially rising waveform here, and some slightly more blurred replica of it here, and so on. And if you cascade enough of these things, the solution to what the output voltage does is the solution of a diffusion equation. And essentially, you think of putting electrons in over here, and they're driven somewhat by the potential difference across these resistors, and they diffuse into this structure. And the further in they get, the slower they go, typically. And in fact, if you make your wire twice as long, once it's in the regime of being limited by diffusion time, the diffusion time will in fact be 4 times as long. So it goes, the time delay is like the square of the wire length for long wires. Fortunately, it's negligible for most wires, but you'll see it's not always negligible. One other kind of delay in wires, which I didn't mention on the chart, but which you might think of, is speed of light delay. That is, on a metal line is really a transmission line. It has negligible resistance, but it has some slight inductance, as all conductors do. This thing propagates a signal much more quickly than the resistor capacitor transmission line. And in fact, you get some reasonable fraction of the speed of light. The reason I didn't mention that is because chips are fairly small, and in current technologies, the speed of light is not a limitation. And I haven't really figured out when it will be. But wouldn't be surprised if it starts coming in. Severo?
I noticed in one of your earlier diagrams when you wanted to go from green to red that you went through a blue layer. Was that an attempt to... When do you do that?
Yeah.
When you have the space?
In a stick diagram, if you want to connect green to red, you draw a black blob. And when you actually implement that, most commonly, that's done by going through the blue layer. There are technologies with a trick known as buried contacts, which allow you to directly connect green to red without coming up to the metal layer. We don't typically use that, and most of our stick diagrams don't indicate that it's done one way or the other. Okay?
The blob is big, though, physically, so you don't tend to use that to shorten the to speed up lines?
To speed up lines.
When do you, I think, as I understand this question, it's
Oh.
saying, when do you go to metal instead of staying in poly?
Oh, you want to know, in order to speed up a line, should you change layers, run it on the metal layer?
Not good.
Yeah, you can do that. In fact, I'll show you. I've done that quite a bit in one of the circuits I'll be showing you on the 4th day. I run metal where I could have run poly all the way.
Can you say what the deciding factor is? Is it a size thing?
Well, in this case, the line in question was the clock line on the fast part of my logic, and I wanted to really get the speed. And there were some other places where I ran long poly lines because the speed didn't matter. So usually, once you identify the core limiting part of your design, you can decide whether to go to maybe a larger area in order to get onto the metal layer. Okay, other kinds of delays. In pass transistors, again, the delay is going to be proportional to the square of how many transistors you have in series. And in fact, it's the same model. Every transistor in series is some series resistance. But typically, you might think of this as a string of transistors, each one of which has a gate, which is a capacitance to ground or to some voltage that's driving it. So it's really the same model, except you can think of the capacitance being sort of distributed over the resistor. But it's all the same thing. You can break it up into a pi section RC delay. Yeah.
Is there much difference in the delay? In other words, it looks like the delay through that might be considerably faster than the delay to turn one of them on and off.
Yeah, you're right. In fact, the delay through 2 or 3 pass transistors can be considerably faster than the rise time of a node driven by a gate. That's why they're useful. They're not, by any means, they're not slow unless you get too many. But too many comes on very quickly because that speed is going up as the square of n. So typically about 4 of these things in series, and then you want to go through a gate. And the combination of those, there's, you can do some optimizations in that line. That's mentioned in the text also. The third kind of delay is another case of the fan-out problem again. That is, suppose you want to get a signal off chip. We haven't talked specifically about what the numbers are for the capacitance of a load on the chip, but they're really small. And compared to, say, a 10 picofarad scope probe that you want to look at something with, you put that on a node, it's going to slow it down by a factor of 100 or so. So somewhere you have to accommodate a fan-out on the order of hundreds. And that's just going to make things very slow, and it's not something you want to do when trying to get a signal off a chip. So instead, we use multi-stage buffers, each stage of which has some medium fan-out. And again, there's an optimization you can do, which is discussed in the book. It tells you what fan-out is best to give you the best speed. And the kinds of buffers we use are regular inverters, or these other things called super buffers, which we'll get into tomorrow, which are a little bit faster. And this is also useful for driving large loads on your chip. For example, you might have a clock line that goes to 100 devices. And so again, there's a fan-out of 100. To accommodate that, you want to use a multi-stage buffering device. So these are the kinds of sort of second-order considerations you have to get into when you put together a system, which you don't need to think about initially when you're designing the logic for the core cells of your processing functions. Okay, let's take a look at what the homework problem is. So I'm getting close to the end of the time. Getting close to the end of my notes. Can we get those handed out?
Where are they?
Well, they were right up. Here they are.
Well, you start talking about that.
We have 2 homework problems. One was mentioned in the outline. That's the first one. It says construct a stick diagram for an nMOS structure implementing a 4-input prioritizer as described below. This is, I think, a really neat problem, which Lynn made up as the sort of first problem for her class at MIT, and it went over really well. Got some very imaginative solutions. This is not a trivial problem. It may be trivial to find a way to do it with, say, gates out of a TTL catalog or something. But to get any kind of a reasonable solution to this, probably based on switch logic, it's going to require some creative thinking and some working with geometric constraints of lines that shouldn't cross each other unless you intend some function. So it's really a good problem for introducing you to the notions of red, green, and blue wires and how they do logical functions. Okay. If you do this with gates, that's fine. You can also do it with switch logic, in which case you may want to add some 0 and 1 inputs and just make a switch network which routes either an input or a 0 or a 1 or something like that to the output. It's not necessarily expected that everyone will come up with a reasonable solution to this because, as I say, it's not a trivial problem. But work on it. On problem 2, you may want to do this one first. Problem 2 is another strictly combinatorial logic function, which in fact it says in the hint is a 3-input exclusive OR. It's a 3-input parity generator. The output is true if an odd number of inputs are true. There's about 1 million ways to go about implementing this thing. Well, I haven't thought of all of them, but I'm sure between the bunch of us we will. So, Peter?
In general, for examples like this, can we assume that we have both the true and complemented form of all the inputs?
In this case, the diagram makes it clear that both the true and complement forms are available. In this case, some solutions don't need to make that assumption. If you do need to make that assumption, just indicate it or draw the inverter that produces it. In many cases, complemented inputs are not available, but it's most efficient to go ahead and generate them and use them that way. Will?
Should we limit ourselves to horizontal and vertical sticks, or are diagonals legal?
Diagonals are legal. I would prefer fairly clean-looking designs. That is, if I want to look at and see if what you did makes sense, I would like not arbitrary angles of things. It would be nice if it had some regularity to it, and there's probably not a lot of good reasons not to stick to horizontal and vertical, but whatever. Any other questions on that?
I just want to emphasize again that you don't need all this stuff about ratios and stuff. Forget it for tonight. It's just
yeah, this is just switch model and loads. Loads if you want to make gates. Okay. Okay. Tomorrow we'll go into more about registers and structures of registers and structured ways to make combinatorial logic, such as programmed logic arrays, and many other interesting digital functions. So let's try and start at 9 o'clock sharp.
Now, wasn't tomorrow the early day?
We're not starting early tomorrow like we had previously assumed, just 9 o'clock.
I did say I wanted to.